Hey, welcome AP students. Sorry, it's the morning. Welcome AP students to your Unit 1 pre-lecture on Intro to Matter. So let's just go ahead and get straight into it. What we see here is that chemistry is the study of matter and the changes it undergoes. We define matter in a very simple way as anything that has mass and volume. That should sound very familiar to basically any like middle school class. Um, how we define matter is through the qualities, or how we define the properties of matter is through the qualities and or features a substance possesses. So we have four main categories, known as extensive, intensive, and they have a secondary term, extrinsic versus intrinsic, you might also hear, and physical versus chemical. These are the four categories that we can label the properties of matter under. So extensive properties are properties that depend on the amount of the substance. So an example might be mass in grams, right? Depending on how much sample you put on that scale, you will measure a specific amount of mass that will adjust accordingly. Okay. It would not be an identifying property. If I told you you had 5 grams of something, that doesn't actually help you know specifically what that substance's identity is. It's a property that can't help you with that. Okay. On the other hand, intensive intrinsic properties are properties that don't, ooh, shocker, that don't depend on amount. And I'm going to abbreviate amount to AMT of the substance. Okay, we really value intensive properties because intensive properties are also often identification properties. We can identify the substance usually from them. So a really good example of an intensive property is actually density. Density is a property that we can use surprisingly to determine what substance we're working with, because usually each substance has its own unique density identity. And so it's something that we use, and you guys, I believe, oh, that's the other class. They do a density analysis lab project, and we replace that with a different one for you guys. So I assume that you all are very familiar with the equation of density. All of you seem to test quite strongly in your mathematics on the pre-diagnostic test at the beginning of class. One thing I want to point out, just as a side note, is we call any value that has 2 units, we say that it's a derived unit. That's just kind of a technical term. You don't have to write that down. This is just something for reference. So for example, density is in grams per milliliter or grams per liter, some unit of mass, some over some unit of volume. And together, the final density value is the composite unit relationship between those two. That is what we call actually a derived unit. So just like a little side note. Okay, let's move on to physical property. So a physical property, well, it is anything physical that you can observe. Physical characteristic. Okay. That's like right observable to the naked eye. Usually observable to the naked eye, right? Um, we say that anytime a physical property changes, it undergoes a physical change. The defining thing about a physical change is that it does not involve, okay? Does not involve or require the change in the identity of the substance. On the other hand, chemical property is really a property based on the chemical nature. It's the chemical characteristic or nature. So I'm going to use a slightly different word because I don't want to write the whole word characteristic. It's the chemical nature of a substance and usually only observed via chemical reaction. Okay. Sorry, there's a lawnmower that I always compete with in the morning. And so we say when there is a change to a chemical property, when there's a change to chemical property, we call that a chemical change. And chemical changes are unique in that they always involve, okay, the change in these substances identity. I.e., we make a new compound. We break old bonds and make new bonds. We rearrange the atoms. We rearrange the elements involved to give way to a completely new substance with, by the way, also new physical properties, right? But the physical property change is the result of a chemical property change. So that brings me to my next point that what we see here is a list of a bunch of examples of physical versus chemical properties, right? These are physical and these are chemical. Be very careful that you do not align physical as being paired with extensive or chemical as being paired as intensive. These are four individual categories. So right here, you have a bunch of different properties or changes or characteristics. And I want you to identify them as physical, chemical, and extensive or intensive. You should have two letters behind each. Use P for physical, use C for chemical, use I for intensive, use E for extensive. And go ahead and try your hand at identifying what type of property categories these would fall under. All right, go ahead and pause me and do that on your own. Okay, so hopefully you pause me and here are the final results. Electrical conductivity is a physical and intensive property. Ductile, the ductile nature, the ability to bend, all right, or actually put into a wire, right, of a metal is a physical intensive property. Being malleable, being shapeable is a physical intensive property. The reactivity of a specific type of substance is a chemical intensive property. The brittleness, how easily it breaks, is a physical intensive property. Magnetism is a physical intensive property. And finally, the heat of formation, the amount of energy it takes to make a new substance, to form a new substance, is a chemical extensive property. So everything in this world is classified as either matter or energy. And we as chemists tend to focus on the matter, but we will have elements of energy involved because what we're going to see soon is that matter and energy are arguably the same thing. Anyone ever heard of Einstein's E equals mc squared equation? That is definitely an important concept that comes into play in this first unit for understanding how we quantify and describe matter. So let's go ahead and talk about the categories of now that we understand what matter is and how we can define its properties and characteristics. Let's go ahead and look at another layer of categorization that we use to describe matter through its nature of being a mixture or a pure solution, as well as the atomic level. So we say for a pure substance, we can often look at a sample at the macroscopic level. We get samples and they are either pure or impure. They are either mixtures or solutions. And so what we say is that a pure substance is defined as, at the atomic level, the particulate level, is defined as a substance with a fixed composition and set of properties that, of course, accompanies that specific composition. Okay, an example would be a single chemical formula substance. Any single chemical formula substance. So I have a sample of alcohol methanol. I have a sample of methanol. Okay, that's a pure substance. If I just pour a vat of methanol, that has a fixed composition. It's just methanol. Okay, methanol is CH3OH. Okay, structure. And this is methanol, just as a little side note. And if I pour you a cup of methanol, all right, to work in one of your beakers as an experiment, that has a single composition and a single set of property because it is only methanol in it, right? We can have elemental pure substances. Elemental pure substances, all right, are substances, okay, at the macroscopic level that are just made of one type of atom. So example, a hunk of iron is technically a solid pure substance. Powder, sulfur actually, by the way, likes to come in powder form usually, and it's actually, we'll introduce later, is actually an allotrope, which means it is a compound made up only of its own atoms. And what we say is that it's purely elemental though, right? It's the same element over and over and over again. This one just happens to be unique in the sense that it bonds to itself. And we would say that it comes in yellow powder form. And if I have a bowl of powdery sulfur, that is a pure powder substance. On the other hand, compounds, all right, you can have a pure substance compound. I just gave you one, right? Methanol. Methanol is a pure substance compound. Okay. It is a compound, which means it involves multiple atoms of different elements bonded together. But my whole sample is a repeat, a large amount of that same characteristic, that same combination of atoms. So in the proper ratio. So that would be an example. Water is one of your most common pure substances that we use in laboratory and you use to survive in life. Okay. If this is feeling a little redundant to you and feeling like this is really basic, good. This is the nice warm up. So mixtures, on the other hand, as you could probably guess, is if you have a sample of matter that is a mixture, we call that, okay, or we define it as it contains a sample that contains two or more substances with different compositions. And the really important thing is that these different substances are not chemically bonded. So it's not just a compound and, oh, look, CH3 is bonded to another set of elements, O and H. That's not a mixture, that's an actual individual compound that is chemically bonded to one another, therefore acting as a new identified species. All right. Here, though, with mixtures, we obviously do not see that. So we can define mixtures as homogeneous or heterogeneous. So if you're at all familiar with the Latin, homo means same, right? And hetero means different. So a homogeneous mixture is a mixture with an even distribution. Okay. And I'm just going to leave that, an even distribution at the particulate level. Which means often, by the way, they almost act like a pure substance because they seem to have the same composition and properties. We call a homogeneous mixture a solution, and a solution is connotatively saying, in the chemical world, connotatively speaking, only applicable to homogeneous mixtures. You would never call a heterogeneous mixture a solution. Okay, so a solution is another term okay, for homogeneous mixture. So one really good example of a solution is after stirring your coffee and your creamer. You no longer can separate the two different substances with different compositions once you have mixed it, but you also know that they are not chemically bonded. You have not created an entirely new liquid sample. You have simply mixed two things evenly to the point where at the particulate level, they seem to have the same composition and seem to take on the same overall properties that you cannot separate. Okay, so when we look at homogeneous mixtures, we usually have a solute and a solvent. The solute is the substance or the component in less. So this is called the minor component. So in our example, the creamer would be most likely the minor component. My guess is you have more coffee than you do cream. You pour in the cream to the coffee, not the other way around. On the other hand, the solvent is the major component in a mixture. Okay, so that would be the coffee. Anytime you have a solution where the water is the solvent, we call it an aqueous solution. Aqueous solutions will be incredibly important for us as we progress in chemistry because water tends to be the environment that a lot of chemical species are analyzed in, worked with, and reacted in. Okay. Metal alloys are another example of a solid homogeneous mixture, and metal alloys are just a fancy way of saying a mixture of metals. So some examples would be of that, bronze or steel. You cannot tell that there are different elements present, metal elements present, because they have been heated so high and then melted to create an almost same composition, same property mixture that you cannot tell the difference of. Okay, so heterogeneous mixture. It's the exact opposite what you would guess. Heterogeneous mixture is at the observable level often. I should put oftentimes at the observable level, a difference in composition. Okay. And particularly or at the particular level, the difference in composition and uneven distribution at the particulate level. By the way, I get a little faster as the year goes on in my future lectures, as I'm just warming up again. But also, I want to remind you that some of these lectures you really should, and I think I'll put these in the description, you should play at 1.25 times speed and you should not write everything down. You should write keywords down. All right. I'm just doing this as a fail safe for all students who work at all different levels, who need all different levels of support and access to notes. But I do hope that as you've been watching this, that you're figuring out very quickly that there's a lot of ways you could shorten this in your writing and that you could speed this up very easily if you're okay with a bit more of a Minnie Mouse voice from me. That being said, I have kind of very little to say about heterogeneous mixtures because they're really obvious usually. So for an example would be trail mix. Right? You can see the individual components with their individual properties in there, right? Your M&Ms, your little dried fruit snacks, your little nuts, or a salad, right? All of these things are heterogeneous mixtures. There's a unique subcategory though under heterogeneous mixtures known as suspension mixtures, where we see suspension, and this is a mixture whose components settle over time. So for a lot of you, that would be like your protein powders. Have you ever had a protein powder and you shake it in the bottle before you go out on your workout and it looks homogeneous? It looks homogeneous. And then you notice, oh, there's a lot of little grainy stuff at the end and you have to chug that at the end and it's really, really gross and grainy. Yeah, that would be an example of suspension. Oh, I definitely meant to say protein powder. Protein. Right? A lot of your whey protein mixes. Okay. So that's all we have for today. Tomorrow, we're going to look at how we can, in the laboratory, separate mixtures and analyze physical change particularly. And then we're going to move into defining more at the particulate level matter and investigate compounds and how we quantify and determine the ratio of atoms in a compound that is chemically bonded, atoms chemically bonded to create a compound. And good job, you guys. I'm looking forward to starting off the year with you. Bye.